Okay, so the class for today, we're going to discuss a new standard called the Web Ontology Language. So the last time we spoke about logic, we started to talk about RDFS, RDF schema, which is a way of representing logical-like statements within RDF graphs. So we saw that RDFS has four main features: subclass, subproperty, domain, and range. And we saw some examples of those in the lab. So in today's topic, we're going to discuss again the logical part, and we'll continue in the next couple of classes to talk about this. But we're going to discuss a much more detailed standard than RDFS called OWL. Okay, so OWL in general is a lot more what we would call expressive. We can express a lot more things using OWL. So here we have an image of a zebroid. So the idea is that it's half zebra or zebra, half equine, meaning it could be a donkey, a horse, a zebra, I guess, so non-zebra equine. So these are hybrids. So if we take an example of an RDF graph here, relatively simple RDF graph, we see that we have a zebroid, and we have a sire, which is like a horse father. Zach's father is Marty. Zach's mother is Leah. Dam is like the horse version of mother in English. And then we have Zia here to the left. And we see that Zia effectively has the same father, the same mother, the same parents. What might we conclude about Zia?
¿También es un zebroide?
Yep. So that Zia is also a zebroid, right? So, okay, we look at it and we come to this conclusion, but then an interesting question to ask is, how do we come to that conclusion, right? So what kinds of reasoning are we using here? So my claim would be that we're using probably deductive reasoning mostly. So why am I saying that? Because we don't see many zebroids, and essentially we're applying some sort of rules. Okay, maybe we learned those rules inductively, but we're applying some sort of deductive process. But it's not so easy, in fact, to be able to understand how we come to that conclusion if we really think about it. So what sorts of assumptions do we make to conclude that Zia is a zebroid? And what we want to do is we want to somehow enable machines to be able to make similar conclusions. Of course, not just this specific example, but we quickly come to the conclusion that Zia must be a zebroid. But what sorts of premises do we use to conclude that? So we could think that, okay, what we're saying is that if X and Y have the same sire and dam, and Y is a zebroid, then Z or X is a zebroid, right? So if we know that these two share the same parents, and this one is a zebroid and this one is a zebroid, but I don't think we ever learned that rule. Okay, so I don't think that's what we're doing. I don't think it's somehow that we came to this conclusion because we remembered this rule at some stage, this complex rule. I don't think it's hard to say how we come to that conclusion, but I don't think that's what's happening. Maybe we could generalize and say, okay, if they have both the same parents, then they're both of the same species. But I don't think we're ever taught that rule either. It's not that we remember that rule. Maybe it's inductive. I don't know. Maybe it's just that we know that children of the same species, all the children of the same species that we've seen are of the same species in general. But I think in general, if we were to argue it out in such a way that we could explain to machines, what we're basing the conclusion on is based on several smaller level observations, more general observations or more general rules. So that sire is a subproperty of parent. So that father is a subproperty of parent, mother is a subproperty of parent. Then we know that a zebroid has exactly one parent that's a zebra. And we know that a zebroid has exactly one parent that's not a zebra and an equine. So a horse, a donkey, a mule, all these various forms of equines that are not zebras. That a zebroid is a subclass of equine. An equine has exactly two parents. Okay, this one is quite general. Two things cannot be related by sire and dam at the same time. Okay, I'll explain why we need that, but essentially we need to say that Marty is a different animal from Leia, which might seem obvious here, but we don't assume in general, we can't assume that two names refer to different things in full generality. Okay, so with all of these assumptions, you can trust me for the moment, we can actually infer that these sort of logical claims, we can deduce that Zia in this case must be zebroid. So we see that there's actually quite a complex process of reasoning going on. So which of these claims are expressible in RDFS? Any ideas? So the first one, sire is a sub-property of parent. Can we express that in RDFS? We sure can, right? And the second one as well. The third one, a zebroid has exactly one parent, a zebra. No, we don't have a way of counting really, or specifying limits and counts. Nor this one, we can't say not zebra, for example. We can't say not zebra and the equine. Zebroid is a subclass of equine. Can we say that in RDFS? Indeed, we can. We have subclass. Equine is exactly two parents. No, two things cannot be related by sire and dam at the same time. No, we don't have a way of saying that in RDFS. So we can cover three of these things in RDFS. And for the rest, we can express them in this new language that I'm going to discuss, which is OWL. So with OWL, we can say much more expressive things, which allow us to be more specific about the semantics, the meaning of data, which allows machines to conclude even more complex aspects. Okay, zebroids. So what kind of language can we use? Of course, this is not just a language for describing things about zebroids, but if we generalize this, we can see that we can express quite complex semantics for data. So the Web Ontology Language, it inverts its acronym, OWL, was standardized in 2004, the first version, and the second version was extended, OWL1, in 2012. So the most recent version has been standardized since for the past 8 years. Often it's used in, it's used a lot for biomedical ontologies. You can imagine that when you're sharing data about biomedical aspects, about clinical data and so forth, it's very important for the data not to be misinterpreted. It's very important for the data to be consistent. So that's one example of use. So there's ontologies, many different domains. And we can build relatively complex definitions of domains, the terms in a domain, using the standard and make it machine readable. So I'm not going to describe this table in detail, but I'd like to just briefly mention, we'll come back to this later, but OWL is underpinned by something called description logics, which is something like a sort of subset, but also extending first order logic. So I guess many of you will have taken a class on first order logic. That will definitely help with the next couple of classes. But if not, no worries. But for those of you who have taken first order logic, you might have heard that first order logic is undecidable in the sense that finding out if a formula is valid in first order logic is not a decidable problem. So description logics is essentially was designed to be decidable. Right? It's one of the main design principles of the logic is to be able to process it with the machine and know that eventually things will stop. So this is something we'll come back to later, but there's quite a lot of features, and they're all defined in terms of this. One way in which they're defined is in terms of description logics. So leaving that aside for the moment, we'll start with a running example for today. So we have this ancestral family tree here, which refers to, any guesses? This refers to the Godfather, right? So we'll look at some examples of family relations and we'll model them as OWL. We'll define the semantics of those relations using OWL, just to give a flavor of all the different features of OWL. So before we start with that, we just have to talk about two logical assumptions. One of them I referred to earlier, about how we interpret the data in a more general sense and how it reflects the world. Okay. So the first is called the open world assumption. So if we look at this example here, we see that the graph mentions 3 children for Vito. So Vito has child Connie, Vito has child Sunny, and Vito has child Michael. So how many children does Vito have according to this RDF graph? How many children can we conclude that he has in real life? So we see this as an RDF graph because we have subject, predicate, object, subject, predicate, object, subject, predicate, object. Yeah, I add some images and so forth to make the slides look more interesting, but it's an RDF graph. So how many children does he have according to this graph? How many children can we conclude he has in real life if we assume that all of these triples are true? Okay, so if all these triples are true, it seems like a trick question. He has 3 children, right? But in fact, we never assume that RDF is complete, right? So it means that our RDF graph, we should always assume it to be incomplete, which means that he might have more children that are just not mentioned in the data. So probably we should say he has at least 3 children. That's one possibility, okay? So in general, RDFS and OWL, RDFS and OWL, they take an open world assumption. So what this means is that anything that is not known is not assumed to be false. It is simply unknown. And this is sort of in contrast with relational databases, where often we'll take something like a closed world assumption. We'll assume that if some employee is not in our database, then that employee is not an employee of the company, right? So without further information, Vito may have children that we don't know about. Okay, so why, if we consider the web, why would this assumption be important? Is this a good idea to take this open world assumption? So an open world assumption is almost a lack of an assumption. We're not assuming things to be false if we don't know them, right? So it's the more general option. And in general, assuming web data to be complete would be a bad idea, right? Because our web data is never going to be complete. We're never going to have a complete description of the world. And if something is not in our data, we can't conclude that to be false, of course. So, and even, you know, a graph might not even, you know, if something happens more recently, maybe we have a relatively complete graph of, let's say, I don't know, about maybe Nobel Prizes, and maybe it's complete, but then there's a new Nobel Prize or a series of Nobel Prizes, and then our graph is incomplete again, and we shouldn't assume things not in the graph to be false. So it seems unreasonable to assume that the data on the web would be complete, right? So the second assumption, or in fact in this case lack of assumption, is that we do not apply a unique name assumption. So what that means essentially is that we never assume that each name in the graph, like Michael, Fredo, Sonny, Connie, these certainly refer to different people. We never assume that. So if we don't assume that all of these names are definitely referring to different people, then we have to conclude that Vito has at least 1 child, right? Because all of these could be referring to the same child, right? So if we assume all of these triples to be true, under the open world assumption and under the lack of unique name assumption, all we can say is that Vito has at least 1 child. That's essentially all we can conclude. And this is also important. It is, so RDFS and OWL do not take a unique name assumption, which means that 2 or more IRIs may refer to the same thing. So without further information, these children of Vito might all refer to 1 child, right? We just have different names for 1 child. So why is this assumption important for the web? Again, we could argue that if we have different websites, and maybe one website's talking about Chile and another website's talking about Chile, if we were to enforce a unique name assumption, what it would mean is that every website out there has to use the same name, the same IRI to refer to Chile. Otherwise, it would create inconsistencies and problems and so forth, because we would have assumed that those chilies are different if they have different names. And obviously trying to enforce a global consistent naming scheme on the web would be a bad idea in general. It would be against the philosophy of the web, of openness and distribution and decentralization. Somehow trying to organize the web to get to agree on the name of everything would seem to be, there were efforts in fact in this direction, but it's not really a great idea. So we don't take this unique name assumption. Okay, any questions or comments or doubts? Okay, so we can start with our, yep.
Dentro de las especificaciones, me he dado cuenta que nunca mencionamos la dimensión tiempo. No hay algo que diga, este grafo funciona para tal día, tal minuto, tal segundo.
Yep. So that's a good question. So we don't have a good example here, but we could assume that maybe some of these edges have a temporal element. So maybe Vito is, okay, there's a start date, for example. So there are two different ways to do that. One is to model that directly in the data, where we would create an n-ry relation, which says that the father is Vito, the son is Michael, and the date, it would specify a date on that. So we consider sort of the temporal element almost as data, like we would add dates of birth, we would add the start time of an event, of an end time of an event, as if it were just data, right? As if it were any data that we're modeling. There have been also extensions proposed. There's also ontologies for representing time in RDF and in OWL. There have been various extensions also proposed to handle RDF. So some people propose, for example, to annotate triples in certain domains, where you extend a triple with this temporal annotation that you can then apply certain operations on, like you can see if two triples were valid at the same time or not. The standard way to do it in most use cases is simply to represent the temporal information as if it were data, right? As if, yeah. But if you needed something more specific, there are extensions of RDF that can help with that.
¿Esas extensiones son desarrolladas por la comunidad?
Yeah. So in general, semantic web is, there's a community of kind of what we would call practitioners, which would be people who've done startups, industry, and so forth around semantic web technologies. But there's a strong component that's a research community. So I don't know if you know Claudio Gutierrez, for example, but he published a paper on representing time in RDF, which is quite influential. There's been more work since that. And there's a lot of research prototypes that can allow you not only to deal with temporal annotations, but also with any sort of annotation. You could also annotate your triples with scores of confidence, for example, with probabilities, with sources, different types of provenance, various types of information. There are extensions of RDF that allow you to work with annotated triples as well.
Genial, gracias.
Okay. Yep. So, okay, we're going to start with some examples. Look at our examples look at RDFS through the lens of our examples. So, subproperty. If we have Vito as the husband of Carmela, so we've already seen these features, right? This will help us warm up. And husband of is a subproperty of spouse. Then what we can conclude here is that Vito is spouse Carmela, right? If we say Carmela is the wife of Vito and wife of is subproperty of spouse, then we can conclude that Carmela is the spouse of Vito. Okay. So we've already seen this feature before. Subclass, so if we see that Mary is of type woman, then we conclude that woman is a subclass of person, and Mary must be of type person. Okay, so domain, if we have that Carmela is the mother of Fredo, and we have that mother of as domain female, then we would assume that, or we would conclude that if these triples are true, then Carmela will be of type female. So for range, Carmela has son Fredo, has son range male, and therefore we could conclude that Fredo must be of type male. So just get warmed up with the examples. We've seen these features before. So a new feature that we haven't seen before that's new to OWL is the feature called OWL same as. So we spoke about the unique name assumption, or the lack of a unique name assumption, where we always assume, or we never assume that two terms, two IRIs, refer to really different things, different people, different buildings, whatever. We can override that with same as, and we can say that these terms refer to the same, these terms in the data refer to the same real world entity. So here we can say Vito old is the same as Vito young. What does that mean? It means, okay, first of all, that Vito young must be the same as Vito old. And if we have, it's also transitive. So if A is same as B, same as C, then we have A same as C, and so forth. What's more interesting, though, that is if we have some data about both entities. For example, we know that Vito old has grandson Vincent, and Mary is the granddaughter of Vito young. What can we do? We can somehow merge that data, right? So we can form a more complex description of that. Lost my connection for a second. I think it's still connected. Yeah, I'll just go back and share. Okay. Let me see where we are. Great. So, okay, we can merge the data under both the names for the same entity. So what about if we want to say that they're definitely different, right? So what we can use is different from. So the different from relation, we could say that Connie is different from Sonny, Connie is different from Fredo, Connie is different from Michael, okay? And that lets us know that these are really different people. So now we would be able to conclude that Vito has at least 2 children, right? So of course, the fact that Connie is different from Sonny and Connie is different from Fredo doesn't mean that Sonny and Fredo are different, right? So we still just have this sort of 2, right? So it's still possible that these 3 people still refer to the, or these 3 names still refer to the same person. Okay, so I was going to ask the question: how many children does Vito have according to this RDF graph? Vito has at least 2 children. That would be our answer now. So we don't assume these things by default, but we can state them if we know them. Different from and same as. So we can have inconsistency in OWL. So what this means is we can say 2 things that we're quite clear are a conflict, that are a contradiction, right? So in general, what will denote an inconsistency with false, and it means that there's somehow a logical contradiction in the data. So Vito old, if Vito old is the same as Vito young, Vito old can't be different from Vito young at the same time. So there's various ways we can have inconsistencies and contradictions in the data that we'll see. So what happens if there's a contradiction? The world will implode, and that'll be the end of civilization. So we'll move on to some property axioms in OWL. Any questions or comments? Okay, so property axioms in OWL. So we have equivalent property. How does this work? It's like a bidirectional version of subproperty of. It says that there are essentially 2 names for the same binary relation. So if we think about it for a second, we might think parent of and has child is just 2 different ways of naming the same relation, right? So here we have Vito parent of Michael, and Michael has child Mary. So if we say parent of is equivalent property has child, what can we infer? We can infer not only that Vito has child Michael, but we can also infer that Michael parent of Mary. So one thing to note is just that the direction of the relation remains the same. Okay, so in both cases, what we infer is the same relation, same direction of relation as the original relation. So we say essentially parent of and has child are 2 names for the same relation. We can look at inverse of. Inverse of is quite similar, except for we flip the direction of the relation. So Carmela, parent of Sunny, Vincent, child of Sunny. So if we think about it, we see that there's obviously some sort of semantic relation between these two relations, parent of and child of. And in fact, that's an inverse of relation. So if we say parent of inverse of child of, and we have Carmela, parent of Sunny, then we can, Vincent, child of Sunny, then we can say Sunny, parent of Vincent. Not only that, but we can say if Carmela, parent of Sunny, then Sunny, child of Carmela. Okay? So we infer in both directions and we flip the direction of the relation each time. So a similar feature is symmetric property, which is in fact a class of properties. So for example, if sibling is the inverse of sibling, we could define this. It would be one way to define it, but another way is to define sibling as a symmetric relation. So if Connie is sibling Fredo, and Fredo is a type symmetric property, then Fredo will be sibling Connie. Okay? So we could equivalently have defined that as sibling inverse of sibling. Okay, but we rather express it in general as a symmetric property. Okay. So the next feature we have, which you may have heard of, are transitive relations, transitive property. So for example, ancestor of. So if we say Carmela is the ancestor of Michael, and Michael is the ancestor of Mary, and then we define that ancestor of is a transitive property, then what happens, essentially we can infer that Carmela would be the ancestor of Mary. Okay. So this is transitive property. Slightly different but related example is the property chain axiom. So like before, okay, sorry, let's look at the example. Sunny, brother of Michael, Michael, parent of Mary. So in some sense, we probably want to infer a relation from Sunny to Mary, precisely like we did before in the transitive property case. But in the transitive property case, this relation is always the same. X ancestor of Y, Y ancestor of Z implies X ancestor of Z. In this case, each of the relations will be different. We have a brother of relation, a parent of relation, and we have, we want to apply here niece, an uncle of relation, sorry. So in this case, we need a property chain axiom, which says uncle of is composed of a list of sort of a path of relations. And we can give a list of one or more relations here. So in this case, we say uncle of is like visiting brother of and then parent of. Okay. So from this, we can conclude that Sunny is the uncle of Mary. Okay, it's a time, I guess, for a break. So here I'll just note that this means new to OWL version 2. I think there's quite a few more property axioms to go, so I think we'll take a pause for 10 minutes. Let me see. Okay, so we spoke about property chain axiom, which allows us to infer the uncle of relation. So this is new to the OWL version 2. I'm not going to talk about it in general, but if you see a 2 in the top right corner, it means that it's something new to the newer version of OWL. A reflexive property. This one's a little bit strange, but we can define, for example, similar to be a reflexive property, which means it's a relation that holds reflexively for everything. Okay. This is more useful often in conjunction with other definitions, but what it means effectively is that everything is similar to itself. So Connie is similar to Connie, Fredo is similar to Fredo, not just people. Chile is similar to Chile, Godfather is similar to Godfather, Mafia is similar to Mafia, and so forth. So reflexive property. So it seems a bit strange, but it can be useful in the context of more complex definitions. Okay. So functional property, from databases, we might remember the idea of a functional dependency that essentially, if we know A, then we know B. So if we know the root of a person, then we know their name, for example. So in this case, it's similar. So it's a functional, it's essentially something like a functional dependency or a functional relationship, a functional property. If we know the biological father of Fredo, if we know Fredo, then we can somehow know, or you can have at most one biological father. Okay. So in this case, if we have two biological fathers, what we can infer, rather than infer a contradiction, we don't have a unique name assumption. We can rather infer that these two names are two names for the same person. Okay, so if we define then that has biological father is of type functional property, then we can infer that these two entities are the same, right? So essentially, this is based on the idea that it has biological father is a functional property, which means that something can only have at most one value for that property. Given that we don't have a unique name assumption, we don't give a contradiction, but rather we assume that they're two different names for the same entity. Okay. So why not say has father was functional? Again, this refers to the same cases, the mayors, and there's certain exceptional cases, of course. For example, Tom Hagen is the adopted son of Vito. So we could say quite reasonably that he has two fathers. And of course, there could be gay couples who have adopted children and so forth. So when we define our ontologies, again, we have to be careful to make sure that somehow we're not limiting its possible use. So inverse functional property works in a similar way, but inverted, flipped. So we flip the direction of the relation. We see that this is a very similar example, just that the direction of the relation is flipped. In this case, we can say biological father of is of type inverse functional property. So if we have has biological father, we say that it's a functional property, and then if we were to find biological father of, the inverse of has biological father, then we could actually entail that biological father of as an inverse functional property. So it's essentially the same concept, but it just says that somehow the value identifies the things related to it, right? It's almost simply the inverse direction. So in this case, we infer something similar. We don't infer inconsistency, but rather under the lack of unique name assumption, we assume that these two entities are the same. Okay. A slightly more complex, but relatively intuitive feature is has key. Okay. So we can define somehow that instances of a certain class are defined by a certain set of properties, by the values on a certain set of properties. So we have this rather strange class called singleton, which I'm going to refer to as a sort of a lone birth. So you're not a twin, you're not a triplet, you're not born together at the same time with your siblings, you're born alone. So for singletons, we can say that they are identified by having a biological mother and the date on which they were born. So in general, if we have a singleton, two singletons that have the same biological mother and were born on the same date, as we have here with Connie and Constanza, then it seems safe to conclude that these are actually, again, two names for the same entity. Okay, of course, this would not apply if these were twins, right? So for this reason, we have to make sure that they're not an instance of a twin or a triple. We have to make sure that they're an instance of a singleton. Without this information here, this key would not hold. Okay, so like we had a reflexive property, we also have an irreflexive property, which says that something cannot be connected to itself with this relation. So we can say, for example, has brother is an irreflexive property. If we have that Fredo has brother Fredo, and we define that has brother is irreflexive, then we end up with a contradiction and civilization as the world implodes. Okay, so in terms of asymmetric property, we saw symmetric property previously, and in this case, what we're saying is that if S has father O, then O cannot have father S, right? Somehow this sort of thing cannot happen. So we can define has father to be an asymmetric property, which bans somehow, or says that such cases would be inconsistent. And we infer again an inconsistency, contradiction. Another way of having a contradiction at the level of properties, we can define properties to be disjoint. And what that means is that the pairs of entities that they relate must be disjoint. We can't relate the same pair using, not even a single pair can be related by both of these properties. So if X has father Y, then we can never have X has son Y. Or if X has son Y, we can never have that X has father Y. So we define this using disjoint property, disjoint property with. So we say has son disjoint property with has father, and we again conclude a contradiction. Okay. So as a last property axiom, this one's a little bit different, but what we can actually do is something like negative triples. We can say this triple does not hold, which is slightly awkward to say in RDF, because we have to somehow negate a triple, which requires this fourth term, which is, what's the symbol here? This is often used for logical negation. It means not. So we say that Fredo does not have the mother Connie, and Fredo has mother Connie. So this is going to be a contradiction. How do we write down this statement here? We need to write down this slightly strange form here, where we say somehow this is a negative property assertion. We say that the subject is Fredo, the predicate is has mother, and the object is Connie, and it will then be negated. Okay. So then if we say Fredo has mother Connie, what happens again? We have a contradiction. Okay, so we say the triple is both true and not true at the same time. And this creates a contradiction and inconsistency. Okay, any questions or comments or doubts? Okay, so we can try to have a look at some axioms, some questions. What would be the inverse of the property father of? Any ideas? This question is slightly a trap. So if we think about it, maybe we might say child of, right? But what it would mean is that if we were to say child of, then if A is child of B, then B would be father of A. And clearly that wouldn't hold, because B could also be the mother of A. So the inverse of child of would be parent of, or the inverse of parent of would be child of, but we can't say that the inverse of father of would be child of. That wouldn't seem to make much sense. So inverse of the property father of would probably be something just boring like has father, okay? Name symmetric property for family relations. So it could be something like sibling. If A sibling B, then B sibling A. Could be cousin, primo. Could be A cousin B, B cousin A, and so forth. A transitive property for family relations. So we saw ancestor of. We could also maybe think of descendant of. Just the inverse of ancestor of. Trying to think of something else. Can't think of anything. We can't do sibling, because if we do sibling, then we would end up with, if A sibling B and B sibling A, then we would end up with A sibling A, which is arguably not correct. Yeah, I can't think of anything else. Maybe you've got some ideas. Property chain axiom for has niece. Niece being sobrina. So has niece. Okay. So the first thing you would need is has sibling, has brother, has sister. So has sibling. And then you would need to follow that with has daughter. Right? So has sibling followed by has daughter. A symmetric property for family relations, and asymmetric property for family relations, sorry. So we saw father of as being an asymmetric property. Mother of, what else could you have? Grandfather of, grandmother of, great-grandmother of, great-grandfather of, great-grandchild of, and so forth. Not sure if there's any more interesting examples. I can't think of any right now. Name a functional property for family relations. So functional property for family relations, we saw has biological father. Other examples, has biological mother. Maybe not so interesting. Has biological grandfather would definitely not be functional property because people can have two biological grandfathers. So we need relations that only have one. Maybe a more interesting case would be has twin sibling. So you can only have one twin sibling. Yeah, I can't think of any more interesting examples. Oh, there was something in the chat, but I can't seem to open the chat right now. I'll have to check it later. So I guess maybe it was a suggestion for an answer. Okay, so hopefully these all make more or less sense. Any questions or comments or doubts? Or any proposed solutions, other alternative solutions? Okay, so we can then talk about class axioms. So we talked about property axioms, which is defining the semantics of properties. Likewise, we can define the semantics of classes, relations between classes. So the first thing that we can do, which is perhaps quite obvious in a way, is to define a bidirectional version of subclass. So we can define equivalent class. So if Vincent is of type human and Mary is of type person, we can see that we're kind of saying the same thing in two different ways, right? These two classes are equivalent. So if something is a person, then they're a human. If they're a human, then they're a person. So this is, we can specify this is human equivalent class person, which means essentially human subclass of person and person subclass of human. Okay, and this will allow us to infer that Vincent is of type person and Mary is of type human. Okay. So like we had disjoint properties, we can also have disjoint classes. So if we say that Vincent is a mafia boss and Vincent is lawful, okay, we see that maybe there's a contradiction here, especially if we define that mafia boss is disjoint with lawful. So it means that if X is an instance of mafia boss, then X cannot be an instance of law-abiding citizen, lawful. Okay, so it means that we can't have an instance of both. So what happens in this case? We infer a contradiction. In this case, the world doesn't explode for some reason, but okay. As another example of something we can infer based on disjoint with, if we have that Vincent is of type mafia boss and Mary is of type lawful, and we know that mafia boss is disjoint with lawful, what could we conclude in this case? Any ideas? So we could conclude that if these two people were the same, it would create a contradiction, an inconsistency. And we always try to avoid inconsistencies where we can. So we try to give whatever explanation doesn't arrive at an inconsistency. Okay. So what does that mean? It means that the only logical conclusion is that these two people must be different. So we can say Vincent different from Mary, and we can also say Mary different from Vincent. Okay. Because if they were to be the same, which is the only other possibility, okay, then they would create an inconsistency. And we always want to try to avoid inconsistency. So we'll come up with the only other logical explanation. Okay, so there are the two class definitions. That was quite short. So we have equivalent class and disjoint with. So also from RDFS, we have the RDFS subclass of class axiom. So these define somehow the semantics or relations between classes. They define things about classes. Any questions or doubts? No? Okay, so the next part is perhaps the more complex part of the standard. It's for defining classes, not defining things about classes, but actually defining new classes. So I'll explain what I mean by that. So here there's some reference to some of the symbols. I'm going to have to use some of those symbols. So we're going to be talking about these elements here. So I'll try to explain those symbols as we go. So some logical symbols. If you've seen first order logic, some of these would be familiar too. Or even set theory. So for example, this is an intersection symbol. So what this means here is subclass. And what we're defining is that mother, it's a new class that we're defining to be, or we're defining mother, sorry, to be the subclass of this new class, which is defined to be the intersection of female and parent. Okay, so we say mother is effectively, if something is a mother, then it is both a female and a parent. Okay, so this symbol here refers to subclass, this one here to intersection of classes. If we have Carmelas of type mother, what could we infer? Well, we can conclude that Carmela is of type female and Carmela is of type parent. Okay, so how is this written down, this definition here? We see in Turtle that what we write is mother subclass of, referring to this thing here, the intersection of a list of classes. So we could actually have, we have two classes here. We could have 3, 4, 5, 6 classes as we prefer. So we infer then that Carmela is of type female and type parent if Carmela is a mother. Okay. What about in this case? So what have we changed? We've changed the symbol here. So we no longer use subclass of, but we rather use these 3 lines here, which denote equivalence. So rather than saying just that mother is contained within this class here, we're saying that these 2 classes are equivalent, right? We're saying that female and parent is equivalent to the class mother, right? And mother is equivalent to the class female, female and parent. So this is our definition here. What changes is instead of having subclass of, we now have equivalent class. So instances of this, we can infer to be this, and instances of this, we can infer to be this. Okay. So if we now say that Carmela is of type female and type parent, what could we conclude? We could conclude that Carmela is of type mother. Okay. Hopefully that makes sense. So we're defining a new class here, which is a class that's the intersection of female and parent. Okay. And then we use a class axiom, an equivalent class to relate it to this other class mother. Okay. So if we have intersection of, it seems obvious that we should have union of, right? So we can say that a person is equivalent to the class that is either criminal or lawful. So here we're assuming that animals can't be criminal or lawful. It's only a categorization that applies to people. Okay? If that were not true, we shouldn't say this, or if we didn't hold that to be true, we wouldn't say that. Okay, so we have criminal and lawful. So if this says that if something is criminal or lawful, then it's a person. If something is a person, then it's criminal or lawful, or both at the moment. So if we say Vincent is lawful, we can entail or infer that Vincent is of type person. Okay. What about if we do it the other way? So we see we have this equivalence here, which allows us to do inference in both directions. So if we say Vincent is a type person, what can we infer? So we can infer that Vincent is a criminal or is lawful, but we don't have a great way to write that down, right? It's not that we can add this relation directly because it's one or the other, but we don't know which. It's actually quite similar to what we saw with the zebroid case. We know that one of the parents must be a zebra and one must be a non-zebra equine, but we don't know which, right? So somehow there's now 2 possibilities we have to consider. But the fact that those possibilities exist is additional information from which we could conclude some other information. So in this case, we can infer that Vincent must be either lawful or criminal or both. Okay, but there's no direct way to write that down in RDF. So what if we wanted to say that it's really an XOR? So it's either a person is either a criminal or lawful, but cannot be both. We have a feature called disjoint union of, which basically states that that it's the disjoint union of these two, and that a person cannot effectively be both of these. So if we have this similar case here, then we can infer that Vincent must be either lawful or criminal, but cannot be an instance of both at the same time. So disjoint union of. So this is like a shortcut, an abbreviation. And if we think about our definitions of sets, aside from intersection and union, we can also talk about complement of. So this is sort of the negation of sets. So we can say dead is equivalent to not alive. Okay. So what does this mean? It means that essentially the class of dead is precisely the class of not alive. Right? So if we have, for example, that Mary is of type alive, then we can infer that Mary is not of type dead. Okay? So Mary is alive, Mary is not dead. Right? On the other hand, spoiler alert, I hope everyone maybe is already aware of what happens here, but if Vito is dead, then we can infer in the other direction that Vito is not alive, right? So it's this bidirectional thing again. So what we actually define here is a partition of all of the entities into two possible classes, dead or alive. So it doesn't matter if it's a person, if it's a table, if it's whatever type of entity it is, it can be classified into either dead or alive in this case. So, okay. We can define a class based on all of its elements. So we can define, for example, that the class Godfather is defined by these three elements here. A better example that's maybe not keeping with the running example would be to define the class of United States as the 50 states of the United States. Or to define the class of Latin America as by naming all of the countries of Latin America. But in this case, we have Godfather is defined to be Vito, Michael, and Vincent. Okay, so we use this in Turtle. Our syntax will write one off. Okay, so Godfather equivalent to this collection of entities here. So there's lots of things we can infer from this, but the most basic thing is that all of these elements here of the class are instances of the class, right? There are some more complex inferences that we'll have to come back to, or I'll show some examples later. But okay, we can infer at least this for the moment. All values from, probably of all of the features, the least intuitive for a reason that I'll explain in a second. But what we're defining here, if you've seen this before, if you've not seen it before, it means for all. You can read this as for all. And the way to remember it is all, it's like an upside down A, okay? For upside down A for all. So we have person is a subclass of for all has parent person. So again, we have subclass. So what this means is that if something is a person, then all of its parents are persons too, okay? So that's relatively intuitive, hopefully. So if we know that Mary is of type person and Mary has parent Michael, what can we infer? Based on this definition, we can infer that Michael must be a person. Okay. So we say here that people, if something is a person, then all of its parents are persons. Okay. So if Mary is a type person, has parent Michael, then Michael must be a person. So there's a slightly unintuitive case here, which I will try to explain with this example, which is maybe not the best, but what happens here is I've changed this to equivalent class. And what I've said now is not just that a person has all parent persons, but also if all of the parents of something are persons, then that thing is a person, which seems safe enough to define. It seems relatively sensible. The problem is that since this is a for all statement, if we know that there's something that has no parents, then it satisfies this definition. So for example, we have that Choppy is a lawnmower, and lawnmower is subclass of has no parents. Okay, so essentially lawnmowers have no parents. Choppy is a lawnmower, therefore Choppy cannot have any parents. And it's sort of trivially speaking, what happens is that since Choppy cannot have any parents, we infer it to be a person. It's because Choppy cannot have any parents, trivially by the definition of this for all statement. Since Choppy has no parents, then all of Choppy's parents are people, trivially, because there's no parents to check. So trivially, it satisfies any for all condition. So that means that we have to be careful. So in general, it's not a good idea. It's very rare cases would you use equivalent class with all values from, because of this vacuous case, this trivial case of something has none of that thing. So something has no parents. Something has no parents, then it will satisfy this class definition here, and then we'll infer it to be whatever is on the other side of the equivalence class. So it's quite rare that we would use equivalence class with all values from. Okay, so maybe a slight complication there. So if we have all values from, we might imagine a natural counterpart would be to have some values from. So this means that if something is a parent, for example, then it has a child that is a person. Okay, so we assume parent is a human name, which is maybe not the best assumption, but okay, in this case we'll assume it. So Michael has child Mary. The Mary type person. What would this entail? In this case, it entails, since Michael has a child that's a person, Michael must be a parent. Okay. So what about if we go in the other direction? We have an equivalence class relation here. So what if we know that Michael is a parent? Well, what we can entail is that Michael must have some person, some child, and that child must be a person. Okay, but we don't know who the child is, right? So it's something existential. So we could use for example, a blank note to represent that. So blank notes represent something that exists, as we discussed in the previous class, but we're not able to name them or assign them an identifier or an IRID because we don't know who they are, right? Or we don't know what the value is. So we can say Michael has some child, and that some child must be of type person, but we don't know the identity of this child. Okay. So we have has value. We're nearly there. We've almost done all the features. Person, subclass of has value species Homo sapiens. Okay. So what happens here, if we know that Mary is of type person, then we can infer that Mary must have the value Homo sapiens on the property species. Okay. So somehow we're saying person implies having this value for this property. If we go in the other direction, and here we have subclass of, but if we define this as the equivalence class, now we can go in the other direction as well. So we can define, for example, that if Mary has species Homo sapiens, then Mary is a person. Okay. So has value. Has self. Essentially, this defines that if something has some relation to itself, then it's an instance of a class, for example. So we say here a narcissist. If something is a narcissist, then it loves itself. Okay. So for example, if Michael is a narcissist, then Michael loves himself. Okay. We can also try to do that in a sort of equivalence class relation. So if we generalize this and say that actually these two definitions are equivalent, then if we know that Michael loves himself, we know that Michael is a narcissist. Okay. So this is the has self definition. So there's two other categories of definitions. There's cardinality restrictions, which define a class with a given number of values for a property. Okay. So for example, we can have an exact cardinality definition where we say that a person has precisely two biological parents, okay, defined here in turtle and owl. We can have a max at most. So we can say a monogamous, someone who believes in monogamous marriages, will have at most although there might be exceptions to this, I guess, but we'll define here that a monogamist has at most one spouse. Maybe they're not married yet, but if they are married, they have at most one spouse. We could define a min relation. So we could say that a parent has at least one child, which is actually very similar to the some values from definition. Okay, so we can define that a parent has at least one child. So we have an exact max and min version of cardinality. So in this case, we don't care what the, oh, I'm quite being, sorry. So time is up. So there's not too much left of the class. Any questions or comments? Does it make sense, or are you lost? Or okay, so there's a little bit more to we're pretty much finished. So we'll continue. We'll finish the class on Wednesday, the last part of the class. So we've seen actually these are the almost the last features that we'll see. So in the lab on Wednesday, we'll look just at the property axioms. We'll have a couple of labs to practice without. So yeah, so the goal overall is that we can define much more rich, complex expressions and semantics in the data. So any questions, comments? Okay.